You know, complex math equations can sometimes feel like this totally cryptic code, right? Just this chaotic jumble of letters mixed with floating digits that demand to be deciphered. But here's the secret. It's really not a chaotic jumble at all. It's actually a highly efficient puzzle. And you know what? You just need the right tools to solve it. So, welcome to our explainer on indices, or, as you might know them, exponents. Today, we're taking this whole mathematical framework and distilling it down into a simple, logical toolkit that you can use to crack literally even the most intimidating equations.
So here's the game plan for this explainer. First up, we're decoding base and power. Then we'll dive into the 3 golden rules. After that, we'll unlock the specialty keys. And finally, we'll put it all together for solving exponential equations. Let's jump in.
All right, kicking things off with section 1, decoding base and power. We've got to learn the alphabet before we can write the poetry.
Seriously, imagine writing out 2 times 2 times 2 times 2 times 2 times 2 every single time you needed to run a calculation. It's tedious, it takes forever, and it's basically begging for a typo. And this is exactly why exponents exist. Look at that elegant little shortcut over there, 2 to the power of 7. It's sleek, it's efficient. Exponents are just this brilliantly simple mathematical notation invented to save us time, space, and a whole lot of ink by compressing repeated multiplication. Let's quickly lock in our vocabulary here so we're all on the exact same page. In 2 to the power of 7, that big number at the bottom, the 2, that's our base. The base is the heavy lifter. It's the number that's actually being multiplied. Now that tiny little number floating up high, the 7, that is the power, or the index. The power's job is to dictate exactly how many times the base multiplies itself. So think of it like this. The base is the what, and the power is the how many times. Okay, moving right along to section 2, the 3 golden rules, or the laws of indices.
If there's one thing you should know about math, it's that it absolutely loves patterns. And these laws are a perfect example. The first law, the product law, tells us that when you multiply 2 identical bases, you literally just add their powers. It's amazing. Multiplication downgrades into simple addition. The second law, the quotient law, shows that when you're dividing identical bases, you just subtract the powers. Division drops down to subtraction. And then the third law, the power law, reveals that a power raised to another power, you just multiply them. It's this beautiful, cascading system of simplification that steps really complex operations right down to basic arithmetic.
Let's actually see these rules out in the wild with some concrete examples straight from our source text. For the first law, a to the power of 7 multiplied by a to the power of 4 seamlessly becomes a to the power of 11. You just add the 7 and the 4 together. Done. For the quotient law, a to the power of 7 divided by a to the 4th simplifies perfectly to a cubed. 7 minus 4 is 3. And for the power law, an a cubed raised to the power of 4 becomes a to the 12th, 3 times 4. See? No calculators needed here, just the underlying structural logic of the rules.
Now things get a little spicy. Section 3, the specialty keys. This covers 0, negative, and fractional indices.
I am not kidding, this is absolutely my favorite magic trick in all of mathematics. Any non-zero number, no matter how massively complex or terrifying it looks, if it is raised to the power of 0, it just becomes a 1. A million to the power of 0? 1. X squared times y cubed all wrapped up in parentheses to the power of 0? Boom, 1. It acts as a total instant reset button. So in our puzzle toolkit, whenever you spot a 0 power, you can just smile, cross out that entire messy chunk of the equation, and replace the whole shebang with a nice clean 1.
But you're probably wondering, what happens when the power goes negative or turns into a fraction? Don't panic, these aren't meant to be scary, they're simply highly specific instructions. A negative index does not mean you have a negative number. It's just an instruction to flip the base into a reciprocal fraction. So a to the power of negative 2 just means 1 over a squared. It's basically a location shift. And a fractional index? That's an instruction to find the root. A power of 1/2 is your standard square root. A power of 1/3 is a cube root. Once you know the code, they're just incredibly efficient ways to write out complex commands.
Now, let's see how this all builds when the base itself is negative. Our source material points out a really fascinating rule here. When you have a negative base, the power actually acts like a filter. If the power is an even number, like 2 or 4, it completely eliminates the negative sign. So negative 2 to the power of 4 becomes a positive 16. But if the power is an odd number, like 3 or 5, that negative sign survives the filter. Negative 2 to the power of 5 stays negative at negative 32. It's a really crucial little detail you definitely want to watch out for as you're solving these puzzles.
All right, here we go. Section 4, solving exponential equations. This is the boss fight.
To beat this boss, you need the ultimate cheat code, and it is beautifully logical. If a to the power of x equals a to the power of y, then x absolutely must equal y. I mean, think about it for a second. If the bases are exactly the same on both sides of the equal sign, the only logical conclusion is that their powers are identical too, right? This one singular realization is the master key that unlocks almost every single exponential equation you're ever going to face.
So how do we actually put that cheat code into practice? We've got a super clear 3-step battle plan. Step 1. Manipulate the numbers using your golden rules so that both sides of the equation have the exact same base. Step 2. Once those bases match perfectly, you can literally just drop them entirely and set the exponents equal to each other. Step 3. Solve that newly created basic equation for x. It's a totally straightforward process of taking a massive complex problem and just breaking it down into manageable little pieces.
Let's walk through this with a real monster of an equation directly from our source. Take a look at equation 5i. We have 9 multiplied by 3 to the power of x equals 27 to the power of 2x minus 5. Okay, step 1. Let's find that common base. Well, 9 is just 3 squared, and 27 is 3 cubed. So we rewrite the whole equation using a base of 3. Using our first law from earlier, the left side becomes 3 to the power of 2 plus x, and using our third law, the right side becomes 3 to the power of 6x minus 15. Okay, our bases now match. Step 2. Drop the bases and equate those exponents. Now we just have 2 plus x equals 6x minus 15. And just like that, this daunting exponential equation has elegantly collapsed into standard, everyday middle school algebra. Step 3. Solve for x, and we end up with 17 over 5. Puzzle solved. See, you totally have the tools to do this. And that brings us to the end of our puzzle-solving journey for today. We took what looked like total alien jargon, and we broke it down into bases, powers, and logical laws. But before we go, I want to leave you with a bit of a provocative thought to chew on. Earlier, we defined exponents as a handy shortcut for repeated multiplication, right? Like 2 to the power of 3 is just 2 times 2 times 2. Super easy to visualize. But given what we just learned about negative indices, what does it truly mean, philosophically, to multiply a number by itself -3 times? Think on that. Thanks so much for joining me on this explainer today. Keep questioning, keep learning, and keep decoding the puzzles around you. Catch you next time.